Hi, in this video we'll discuss about difference between the combustion models that are present in Ansys Fluent. So those are finite rate, eddy dissipation model, finite rate, eddy dissipation, and eddy dissipation concept model. So these are the four models that are present in Ansys Fluent. So I'll directly jump into a simple reaction. What you can see, when methane is reacting with oxygen to provide carbon dioxide and water vapor, right? So for this reaction to happen, if you consider a laminar flow, so then you can go with a finite rate model. So in a finite rate model, the reaction rate is controlled by pre-exponential factor, activation energy, temperature exponent, and the reactants power its exponents. So this is a reaction rate. These reaction rates multiply with the stoichiometric coefficient and the molecular weights. So you would get the net species that is added and the net species that is removed. So when the reaction happens, CH4 will be removed, oxygen will be removed, and CO2 and H2O will be added into the single cell. When you are discretized in any domain, so you have a cells. So in single cell, it will check whether CH4 and O2 are present. If these two are present, these would react based upon these numbers, and it gives the products that are CO2 and H2O in the same cell. And that too, if it is laminar flow, this is the way you need to go forward, because in the laminar flow you don't consider most of the turbulence models, so you can go with this particular thing. And if you see, the temperature is low, if the temperature is 300 or 280 or 270, this reaction cannot progress, because E power minus EA by RT. If you see this, if the temperature is low, then the net product or the net value would be very low, because EA will be high, minus of that would give a very high number, E power minus that is very high number, and the reaction rate would be very low. So when the temperature is 300 for CH4 as well as oxygen, when they both, maybe from this point, if the fuel comes and here the air comes, this way also air comes, then these two comes and meet here, then if the temperatures are 300, then there is no reaction or very less reaction due to the temperature point here. This product would be very low. So that is where how you have a finite rate model. So now in eddy dissipation model, so same, what you need to find is RF, what is the reaction rate for eddy dissipation model. So this is the formula for eddy dissipation model. So here we are taking species fraction, and this species fraction is for fuel, this species fraction is for oxidizer or oxygen. So this YF by nu F into MF, which value is low, right? Which value is low, that value is considered out of these two, and that is multiplied with epsilon by K. So I've already listed out what are all the terminology here. You can find out. So what does each thing means? So dissipation, turbulent kinetic energy, all those parameters. So if the turbulent dissipation by kinetic energy, if it is high, then the reaction rate would be high, and that too it will take minimum of these two values. So simply, if you right for time being, if you don't consider these two, you'll check the epsilon by K. Wherever this value is high, then the reaction rate will be high in that specific area, and that automatically gives the amount of CH4 and O2 being consumed in the single cell. But the reaction rate is not dependent on these values, but it is simply dependent on epsilon by K, only pure turbulence. Okay, so that value it will take and it will try to calculate. Now, if you go for finite rate plus eddy dissipation model, till now this is only eddy dissipation model I have discussed. If it is finite rate slash eddy dissipation model, so it will check for this value, it will calculate, and it will also check for this value, eddy dissipation model reaction rate. Among these two, which is lower in value, that would be considered for the reaction rate, and the remaining things would remain same. So CH4 and O2 will be consumed, and the CO2 and H2O will be produced in the single cell, right? So this is three models what we have discussed till now, and there's another model called eddy dissipation concept. So this is very, very important when you have a huge eddies. For example, so from here air is coming, and from this point fuel is coming, again from this point air is coming. So when these three mix with a high turbulence rate, okay, then there comes a area where there will be finer eddies, right? So finer eddies in sense, in a single cell, if you take, we are not considering many cells, in a single cell, so there is a fraction in that single cell where we can say there are very, very fine eddies. But on a whole, we cannot have two different large eddies and fine eddies in a single cell, right? We cannot have a two when you go for a simple RANS model like K omega model or K epsilon model. You cannot have two kinds of eddies in the same cell, right? So in a single cell, you would have large eddies and fine eddies in practical sense. But when it comes to our theory, so how we are representing these fine eddies is the fraction of the cell which is occupied these small eddies, fine eddies, is using this. As you can see here, these are the fine structure scale eddies. This represents the fraction of the entire cell that have these fine eddies, which is dependent on eddy dissipation rate and the K square. So this is the turbulence kinetic energy. Now if you take this value, you will understand how it exactly represents the fine eddies, because this will be of no units, mass fraction. You can see the epsilon star is a fraction, so the fraction will not have any units. So this, if you trace down also, it will have no units. Okay, so this will boil down to no units, and this is the amount of fraction of fine eddies present in a single cell. It's a mass fraction, you can say. And what is the time it can sustain in the inside a cell? So that is given by tau star, which is again having a unit of second. It is having a unit of second, kinematic viscosity. So it is meter square per second, and this dissipation rate, its units. When you integrate here, so you will be get units of seconds. Okay, so this is the time at which the fine eddies can present inside a single cell. This is practical for the simulation or for discretization and doing this simple scheme or simplex scheme. No, it's not possible. So it is an approximation what we are taking. Okay, so now when it comes to here, in this particular fraction, maybe if you take this cell, in this, if you assume this is the area, this is the amount of area, I cannot say is this left side or right side or any side, it can be any side. So in that single cell, a specific fraction, in that fraction, so where there is a fine eddy, right, in that area we'll try to have a Arrhenius rates, that is finite rate. So we'll have a reaction of finite rate chemistry inside this small portion. Okay, so we'll have a reaction inside this small portion. So now the reaction happens in the inside this small portion, mass fraction. For example, X is the CO2 that is produced. But now if this mass fraction is something like epsilon star, so now the mass fraction produced of CO2 is epsilon star CO2. So we need to find these values, right? This is the initially there is no CO2. After reaction, CH4 is consumed and CO2 is added in the same cell, but a proportion with the multiplied with mass fraction. Okay, so now if you take here the species production inside the fine structure, how much species is produced, it depends on the products minus reactants into reaction rate, and this reaction rate is given by a finite rate chemistry. And you can clearly see it depends on Y star and T star. So Y star and T star are nothing but the mass fraction and the temperature of the fine eddies. And how we'll calculate that? So we'll have this kind of species production, and this is the actual change in mass fraction only due to the finite mass, and we will try to assume some values, random values of y star and t star, which get solving these equations. This is for mass and this is for energy. If you start solving this equation, finally there would be y star and t star values which will satisfy epsilon star and tau star, because tau star and epsilon star are already known to us. We'll substitute here, and we have two unknowns, two variables, sorry, three unknowns. One second, sorry, y star is one unknown, t star is one unknown. So two unknowns, two variables. We'll try to solve and we'll get yi star and t star. When these substituted back to our equation, so this is our equation which helps in identifying the reaction rate. So once this reaction rate is identified, so that reaction rate here it is multiplied. Again the same procedure. So now in the previous three we are calculating per cell, but in eddy dissipation concept we are selecting only fraction of cell where the reactions should happen with respect to the finite rate chemistry, and we are implementing that species distribution inside a single cell out of the mass fractions. So now we can see here, so this is the part from which I am injecting fuel, and these are the parts from which I am injecting the air, right? And you can just see here, this is a mixture material what I have taken, and in the mixture material, so these are the species: water vapor, O2, CO2, CH4 and N2. So it's a simple reaction what I am considering. I'll just show you the reaction also. So CH4 plus O2 reacting to give to CO2 and H2O. So this is a finite rate chemistry model, right? And I'll just show you the inlets. Air is at 300 and the velocity of air is 3 meters per second with this as a fraction. So remaining fraction is nitrogen, and the fuel is also at 300, but it is purely CH4, right? And you can see in the species self-selected finite rate model, okay, with the, and this should be laminar, but if you give turbulence also it will run, but you cannot see any reaction rate. Even though there is a reaction rate, it's very minimal. I'll just show it to you. I'll just stop here. Now you can see so there is no much reaction rate, so that's the reason why there is no change in temperature, even though it is exothermic reaction. I can show you the reaction rates also. It's very low, 1 to the power minus 28, right? Now if I increase the fuel temperature, for example, I will make it as 800, or maybe I'll keep this as 300. I'll increase the air temperature, maybe 700. You would see the change. Once verify whether it changed or not. Sorry, it's not changed, so I'll make it 800. You would see change in the reaction rates. So now you can see there is a increase in reaction rate, and you will see also change in temperature. So the temperature is bit huge now. The reaction rate is also good amount, and maybe you can also see how much heat of reaction is added. So you can see heat is added, but I can let it run for more time also. Then now you will see, and the temperature also, and the reaction rate also. You can see the reaction rate initially it is 10 power minus 28, now it's 10 power minus 5. So more reaction rate due to the temperature. Now instead of that, if I go to finite rate Eddy dissipation model with again reducing my temperature to 300. Now you cannot see any reaction rate again because it will take minimum of these two. Obviously it will take minimum of either this one or this one, right? But according to the Arrhenius rates, we know that if the temperature is low, the entire reaction rate is low, so it will take this term for the reaction rate evaluation. And you can see if you take that as a reaction rate, then there will be again no reaction rate, 10 power minus 28. It's very low, nothing you are able to see. Okay, so now if you again turn and go to Eddy dissipation model instead of Eddy dissipation or finite rate slash, then you can see huge amount of reaction because it's again the temperatures are low, but the reaction happens only due to the turbulence, right? So that pronouncingly increases the reaction rates. You can just see here the temperature raise also will be too huge. So you can see the reaction rate is 0.77 max. The temperature is approximately 2200. See, so there's a huge reaction rate, that's a huge exothermic that has been happening. It is due to purely turbulence. Now, if I go with the Eddy dissipation concept model, again the thing is same. Even though there is a fine structure, but there is no Arrhenius rates due to the low temperature, you cannot see any reaction rates. Let's stop and show it. This is all for demonstration purpose. So you can see the temperature is raised 301. It's not too low, but it's okay. It's not too high also. And the reaction rate, you would see it very low. It's also 1 e power minus 28. So there is no much reaction rate happening. And wherever you see increase in temperature, then you can verify. So wherever there is a huge dissipation, right? This is where the dissipation is huge. I'll just show it to you. So you can just check this ratio where it is high, there you can see the reaction rate. Okay, so that is the reason why you will see the reaction rate high here, because the ratio would be high here. Got it? And now in this case also, if you want to see higher temperature, then again you can increase to 800. Then you will see higher temperature in this case also, and that too the higher temperature is due to the specific mass fraction in the individual cell, not on an entire basis, right? Which generally happens in finite rate within the entire cell, but in Eddy dissipation concept it assigns to only specific mass fraction of the individual cell. So there is much time, it will need to run a longer time because I have taken coupled flow, so you need to run more, but the reaction rate will be high enough. And that too, this is correct methodology. Then there is a interaction of turbulence plus finite rate, and there is a reaction rates that to be included accordingly. So you can see it's 80 power minus 6 which is initially very low, 1 e power minus 28. This is happening. So you need to select like according to your specific use case where the turbulence is high or the finite rate is important. Is it a low laminar speed, laminar flame? What exactly it is? Like, so hope this video helped you. And if you want to see more and amount of temperature to be added, you need to run a bit course of time. Then you will get proper readings and everything. This is for only demonstration. Okay, thank you.